And a very crucial idea is the idea of invariance, which people started using in the 19th century. So you've heard about Lagrange points, for example. So people realized doing celestial mechanics that it's very often convenient to choose a different frame. So if you live on planet Earth, you could use the celestial frame where the planet is whipping around, but you prefer to do the local frame and you pay a price which is called Coriolis force. So people realized very early that there are choices of frames that explore the same physics, but there might be natural to the other one. And that's the most crucial thing I'm trying to get to you through this. Just because somebody wrote these equations in some form, so Newton equations are written in Cartesian form in x1, x2, x3 in certain way, and p1, doesn't mean that these are good solutions. A good way of stating the law, and we already did this before, we realized that dynamics is the same dynamics rewritten in any coordinate system. And here we'll do a fairly simple version of this. We will be only doing linear coordinate changes. So we'll be looking at linear actions of groups. So we'll rotate, move, translate, flip, things that can be represented by matrices. So they're linear. It's perfectly okay to change your law by 1930s. Elie Cartan formalized it without thinking about dynamics, just thinking about what's meaning of symmetry. It's perfectly okay to write equation which traces another trajectory in the space. So it's perfectly okay to write a new law. This is x prime of t is f prime of t. There's some coordinate change of this type. And not only that, if you really think about it, you're allowed to make coordinate changes that change in time. As long as you're exploring the same set of hypersurfaces, any representation of dynamics is good enough. So this is called a moving frame. By Elie Cartan. Cartan is very kind to people over 30 like myself, because Elie Cartan is a great mathematician who did great work in his 80s and 90s. And he's probably the only one, but it gives us all hope. So he did his fundamental work in 1890s, and he did fundamental work still in 1930s, which is not bad. We are very happy that he exists. So this will be the central idea. Once you understand that the world that you thought was every point had a meaning is not anymore true. Only group orbits have meanings, because only sets of equivalent states have meanings. So you have to redo your way of thinking about dynamics. And then the second thing that happens is that, yes, there is dynamics, but it's actually very free. I'm allowed to do anything using this symmetry relation at any time, because the symmetry commutes dynamics. So I'm allowed to deform all the orbit in any other orbit that I find natural or convenient for my particular calculation. And so there's a huge set of freedom in this. And now, freedom comes at price. So freedom means chaos, as you might have noticed. So it has an upside and downside. So we are used in physics to say, oh, I have symmetry, this is great. It'll make my problem simpler, because whenever you have symmetry, the number of degrees of freedom that you have to deal with is smaller, because they're all related by the symmetry. But if you're just given to doing what my honorable colleagues on third and fifth floor love to do, which is you run computers. The symmetry is a real nuisance because it will turn out to obscure the essence of your problem. So in book and in your simulations, which you will do on computer, it turns out when you have symmetry and you look some rather simple problems, you get something that looks like this. So this is computer, and then there is the extra cost, which is you listen to me for once. You don't ignore what I say, but just try it. I mean, I might be wrong, but just give me a try. There's an idea, and you discover that this thing is just beautiful once you have used symmetry. Okay, so now that's the thing. The moment there is symmetry, the world is foliated. You have to understand how to deal with that. It turns out this foliation is very difficult to draw because our problems tend to be high dimensional, and even though these things are maybe just loops, the group orbits are maybe tori or some simple surfaces, when they're embedded in 100,000 dimensions, they look very weird. It's not totally obvious how to visualize them, what to think about them. But the mere fact that they're low dimensional is a great thing. And once you understand this, and the next lecture in which we learn how to replace every group orbit just by one point, one representative, then amazing things happen, and you get very surprised because you would think if you have a high dimensional problem and you take care of one coordinate, so you get instead of 1,001 coordinates, you have 1,000 coordinates. What's the big deal? It turns out it's such an intelligent thinking kind of coordinate that things just open up like a treasure trove. And they have opened for me and for some other graduate students and some other collaborators in, let's say, Germany and a few places like that in the past, so I know it works. And they will open for you if you actually do it. But every time you have to, for every problem you have to rethink it because implementation is kind of different in every problem. So that's the general thing. There are surfaces. Dynamics now is not unique anymore. It's just telling you how you go from surface to surface. That's a new freedom. It's called moving frame freedom. The fact that you can do lots of things along the group orbit without paying any cost turns out to give you a very ugly kind of chaos, not the pretty chaos that we like in this course. So the freedom is comes with a high price, and it's only after you learn how to deal with the symmetries that essential beauty of your problem is revealed. But before, it's just a mess.